Hello everyone and welcome back to this next lecture in the machine simulation series. And it has been almost a month since my last video. My old laptop is unfortunately seems to have completely broken down, or at least it is difficult to create videos with it because video editing and video recording is fairly intensive, at least computationally intensive, if not. It requires a lot of resources. So I have managed to salvage another laptop and I am now using it to create this video. Let me see how it goes. It's not the best, but let me give it a try. So to start off with, I will do a little bit of a recap of where we left off, and I will try to introduce maybe one new concept in this video. So before I start, as usual, a little bit of brief background. That if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses which you can find on my own website, which is pythonpowerelectronics.com. That is the name of the project followed by .com. So this is the website of this project and contains almost all the information of this project. I would recommend you to just go through these, and most importantly these 4 buttons. Now in these 4 buttons, if you click on the Learn button, it will take you to the list of courses. So currently I have 5 courses, and the first course is called Simulating Power Electronic Circuits using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate power electronic circuits. The next course is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the SciPy and the Signal package within SciPy to analyze and implement filters for power engineering applications. The third course is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to model and simulate magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package along with Python Power Electronics to analyze and design controllers specifically for power electronics applications, with the example of a single phase inverter connected to a single phase grid. And the very last course I have is called Why Specialize in Power Electronics, and this is a free course which is targeted either towards high school students or towards undergraduate students in order to tell them about the opportunities and challenges available in power electronics so that they may choose power electronics as their domain of specialization. So all these courses are available on 2 platforms, which is Decibels Labs and Udemy. If you click on any of these buttons, it will take you to the link for the course. So the link for this page is available in the description of this video. If you are interested, please do check it out. So with this, let me return back to my lecture. So in the lecture, where we had left off is we were trying to create a model of our induction motor, and we had written some of the electrical equations, and we were trying to build the mechanical equations, because eventually our objective is to link the electrical equations and the mechanical equations so as to be able to produce one complete model of an induction motor. So we had looked at the concept of how electrical torque is produced, and this electrical torque is merely the result of mechanical force which is produced because a current carrying conductor is placed in a magnetic field, right? And to describe that, we can of course go to some of the diagrams we had. So for example, in this basic diagram I talked about how if we have a stator, that is an outer stator, and we had simplified the stator with just 2 slots which carries all the stator conductors, and similarly we had also simplified the rotor to be just 2 slots that contain all the rotor bars if it's a squirrel cage induction motor. And we had said that if these rotor bars carry a current, then in that case, because these rotor bars will be in the magnetic field of the stator, they will experience a mechanical force, and this mechanical force is described in this direction. And similarly, in this, for the lower slot, the mechanical force is described in this direction. So therefore, if there is a mechanical force in this manner, it is quite obvious that it will produce a torque, and this torque will cause the rotor to rotate in the counterclockwise direction. And of course, we can even dig deeper into our diagrams, and we can also say that this concept of a magnetic field interacting on a conductor can be described with this diagram, where this rectangle here, or this wire, represents a conductor which is carrying a current that is in this direction, in the direction of the arrow. Now the concept is, we were thinking that we decided that we can use the Fleming's left-hand rule to determine the nature of force. So for example, let me go to a web browser and let me show you Fleming's left-hand rule. So Fleming's left-hand rule is merely when you use the left hand in such a manner that your thumb, your forefinger and your middle finger are outstretched at 90 degrees to each other. And when they are outstretched at 90 degrees to each other, if the thumb points, or rather if the forefinger points in the direction of the magnetic field and the middle finger points in the direction of the current, the thumb will indicate the direction of the mechanical force. And using this, we can determine the nature of mechanical force in this case as well as for any case. So for example, this is a general case. In this general case, if we consider that this is the direction of the magnetic field and this is the direction of the current, then quite obvious, the mechanical force experienced by this current carrying conductor is going to make it jump out of the page or out of the screen. And if on the other hand we were to reverse any of them, you will see that this mechanical force would cause it to push back within the screen or behind the screen, right? Now the concept is, in this case, Fleming's left-hand rule assumes that they are all 90 degrees to each other. But they need not be at 90 degrees to each other. It is quite possible that maybe the field and the current are not at an angle of 90 degrees but an angle something else. It could be anything else. So for example, coming back to our diagram, let us suppose that this is the direction, this is the magnetic field, right? So this represents a single line that represents all the magnetic lines of force that this current carrying conductor experiences. And you can see that the angle made between this magnetic line of force and the current is not 90 degrees, is some smaller angle. However, in such a case, it is always possible that we determine the magnetic field which is perpendicular to the current by calculating the projection. And this projection is simply the sinusoid of this angle. So therefore, it is always possible, even if our magnetic field is not 90 degrees to the current, it is always possible to determine the projection which is 90 degrees to the current. Now that we talked about this particular topic, we know that whatever may be the magnetic field that is impacting a current, the force is always going to be in a plane which is perpendicular to the plane formed by the magnetic field and the current. So if we assume that this is a plane, so in our case the plane in which these two are interacting is the screen, right? If we consider a two-dimensional plane where the magnetic force is interacting with the current carrying conductor, in which case it actually means that this current carrying conductor is also producing a magnetic field and they are interacting each other. But of course, if we do assume that these two exist on the same magnetic or the same two-dimensional plane, the mechanical force will be perpendicular to it. And to determine this, we've also had several other descriptions. So for example, so this was another diagram that we had drawn. Where we had described this concept. In this case, we had considered a pair of poles, that is denoted by north and south, which had a magnetic field between them. So of course, it's described as a uniform magnetic field consisting of parallel lines of force. And we had considered a current carrying conductor, such as this one, which is producing concentric lines of magnetic force in this direction, which of course you can determine by using the right hand thumb rule. that is, grab the conductor with your right hand, with the thumb indicating the direction of the current, and the direction in which the fingers encircle the conductor is the direction of the magnetic lines of force. Now, if we were to assume that this current carrying conductor was to be placed in this magnetic field in such a way that this magnetic field produced by the current carrying conductor and the magnetic field produced by these pair of poles were in the same plane, right? In that case, we end up with such an interaction. So as we already have seen, magnetic lines of force cannot intersect, which means that when they start coming close to each other, they begin to distort. The distortion is dependent on the direction of the two magnetic fields. Of course, this is a pretty rough diagram, but the main concept here was, because of this distortion, the magnetic field surrounding this conductor gets distorted almost in the shape of an egg. And one can easily see that the egg will be extended in the direction in which the force is produced. So for example, in this case, the magnetic lines of force are getting squished at the bottom and are getting elongated at the top. And quite obviously, the region in which the magnetic lines of force are dense is the region in which the mechanical force is pushing the conductor in the other direction. Therefore, the mechanical force is produced from the bottom to the top. So, in this manner, this is merely a description how we can interpret Fleming's left-hand rule. We don't have to start drawing these flux diagrams every time because we have Fleming's left-hand rule. But what is important to understand in this is that for an effective mechanical force to be produced, the two magnetic fields need to be in the same plane. If they are in perpendicular planes, the interaction is going to be minimal, in which case not much mechanical force is produced. So, coming back to this one. In this case, we say that this current carrying conductor and this magnetic line of force will, if we assume that they are still going to produce, because if we look at these two, if we look at this current carrying conductor, again, according to Fleming's left-hand rule, or rather not Fleming's left-hand rule, to the right-hand rule, will produce a magnetic field which is concentric to this conductor, which is perpendicular to the plane of this conductor, and which is in the direction such that in the same direction as the fingers encircling the conductor. So you can see that it is almost, you can say, counterclockwise if we look at the conductor from the right. So once again, in such a case, because the magnetic lines of force are perpendicular to the conductor, this magnetic field which is perpendicular to the conductor will be in the same plane as the magnetic field produced by this conductor. And therefore, this is when mechanical force is really produced. Now, the question therefore arises, how do we calculate this mechanical force? Because eventually, we need to come up with an equation for the electrical torque. And to come up with an equation for the electrical torque, we need equations for the mechanical force. And in reality, we actually will use another technique, but still, I want to describe this concept of how we can calculate mechanical force so that we can apply it to a physical machine such as this one. So in a machine like this, we can use Fleming's left-hand rule, we can determine the mechanical force, and we can determine the torque through these equations. So before we proceed to that, let's go back here to the browser and let me describe another concept which is called the cross product. So the cross product is a mathematical construct. Well, you can say mathematical or physical construct. Let me look for a Wikipedia. Yes, this is the Wikipedia one. So in mathematics, or you can say physics, right? Because of course physics uses mathematics. If we have two vectors, such as this vector A and this vector B, then in that case we can determine something called as a cross product. The cross product is determined in this, is denoted in this manner, A cross B. So when we say, I think I clicked on something, let me go back, yeah. So A cross B is the denotion of a cross product, is how you denote a cross product between two vectors A and B. And when you denote a cross product between these two vectors, the result is always going to be perpendicular to the plane formed by these two vectors, right? Now, the question then arises, number one, what is the magnitude of this vector, A cross B? And this magnitude, A cross B, is equal to the magnitude of the two vectors multiplied by the sinusoid of the angle between them. Alright? So, if we look at this, if these two vectors A and B are at 90 degrees to each other, the sinusoid of the angle is maximum, which is 1. And in which case, the cross product is the strongest, right? Because then in that case, the cross product is merely the product of the magnitude of the two vectors. On the other hand, if these two vectors are not at 90 degrees, but at some other angle, the sinusoid of the angle is going to be less than 90 degrees and therefore is going to be less than 1. And which means the cross product is going to be less than the product of the magnitude of the two vectors. But you can very clearly see there is an analogy between these two and our discussion here on the cross product, or rather the interaction between the magnetic field and the current carrying conductor. So you see here we had already seen that when the magnetic field is at 90 degrees to the current, the mechanical force produced is maximum. When the magnetic field is at an angle which is less than or greater than 90 degrees with respect to the current, in that case we take the sinusoid of the magnetic field to determine the projection of the magnetic field which is at 90 degrees to the current. And if you look, it's pretty clearly that is what we are doing here as well. When you take sine of theta and you apply it to any vector, that is either to vector A or to vector B, you are merely finding the projection of one vector which is perpendicular to the other. So therefore, it is pretty much coming back to the same concept. Alright? That is, we can again use something like a hand rule. Now, at this point, I'm going to say let us not talk about the actual hand rule because we already introduced left hand rule and there will be a confusion here. But what is important to remember here is that we can use this cross product concept to calculating the mechanical force in exactly the same way by saying that this mechanical force is going to be at a plane 90 degrees to the plane formed by the current and the magnetic field. And once again, the mechanical force produced is maximum when the magnetic field is at 90 degrees to the current. And if the magnetic field is not at 90 degrees to the current, then we can always find the projection of the magnetic field which is at 90 degrees to the current and continue with our calculations. So, if you take a look at this equation, we can readily adapt this equation to calculate the mechanical force on a current carrying conductor due to an external magnetic field. So this is what we'll do in the next lecture. So as before, if you have any doubts about what I talked about or you have any other comments, feel free to either comment or send me an email or message me on social media, whichever is your preference. Otherwise, I'll see you next week where we will continue with this. Thank you so much for listening and goodbye for now.